Okay, so here are the notes for section 11.4, areas of regular polygons and composite figures. So book talks about using inscribed and circumscribed figures and areas of circles and stuff. To some degree, that's what we're going to do. Is we're going to find the area of regular polygons and composite figures, and yeah, that's what we're going to do. So areas of regular polygons. First of all, we need to talk about some definitions in regular polygons. Of course, a regular polygon means all the sides are congruent. Excuse me, all the angles are congruent. Every regular polygon has some special segments. It has a center, which is actually the center of the circle that goes around it, that's circumscribed around it. Same center. The radius of the regular polygon, it goes from the center to a vertex, and the reason it's called the radius is because it's really the radius of the circle as well. Okay. The new part, and this is the important part, it's the apothem, okay, or apothem. It depends on how your teacher pronounced it. Mine pronounced it apothem. So right there, and that made it virtually impossible to see. Made it worse to see. Let's do this in yellow. Maybe yellow make it stand out. Yeah, yellow makes that green color. So the apothem, that is the segment that goes from the center of the circle or the center of the polygon to the midpoint of a side. But more importantly, what it really is for us is it's the height of one of the triangles that gets formed when you cut this guy up. Because that's basically what we're going to do to find the areas. We're going to create a bunch of different triangles by creating all the radii of the regular polygons. And what ends up happening is it says isosceles triangles. That's what's going on. This guy here is all these radii are the same. So what ends up happening is we create isosceles triangles. So the height of one of those isosceles triangles is the apothem. And that's really going to be 90% of your work. Can you find the apothem, or can you find a side length? And to do that, we're going to use what's called the central angle of a regular polygon, which is actually the same thing as the central angle. Whoops, that doesn't work as well as I'd hoped. Yeah, I just don't do that. I'll just draw it out. The central angle really is just the same thing as the central angle of the circle as well, but it goes from here to here. Okay. And so we'll use those, and I'll show you how in a little bit. But here's the first example. Looking at this circle, okay, can you identify the radius, the center, the apothem, and the central angle of the polygon, and then find the measure of a central angle? Okay, so here we go. So here's the figure. Now the center. Hopefully the center is quite easy. It's x. So center is x. A radius, there are two drawn in here. Segment XR and segment XQ. Those are both radii of the polygon. The apothem is again from the center to the midpoint of the opposite side, or it's the height of the isosceles triangle. That's xn. Then a central angle, well, the central angle goes from Q to X to R, so angle QXR or angle QRX, however you want to say it. Now the book has this little nifty formula for finding the central angle. I prefer you just stop and think for a moment. Let's draw in the triangles. If I draw in all the radii, I get 5 triangles. Ignore xn because that's not part of the triangles. Here are those 5 radii. Well, each central angle is congruent. Well, if there are 5 sides, there are going to be 5 central angles. So there are 360 degrees in this guy. Divide them by 5. 72 degrees is the central angle. Okay. If there were 10 sides, it'd be 10 angles. 360 divided by 10, 36 degrees per central angle. So that's really the key to this is later on is figuring out the central angle measure, which in this case is 72 degrees. Okay, so the first formula for this section, actually this is even in the book, this is something that I'm covering and throwing at you, but it's area of an equilateral triangle. And I think it's a formula you really should know. So here's how it works. On an equilateral triangle, all of the side lengths are the same. They're all S. And all of the angles are the same. They're all 60. But in order to know the area of a triangle, it's 1/2 base times height. Well, the base is easy. It's just S. The height, that's the tricky part. Except when I draw in the height, what I do is I cut that base in half. I make it 1/2 S and 1/2 S. And then this becomes a 30, 60, 90 triangle. So this guy here is 1/2 S root 3 for his height. Okay. So area is 1/2 the base, which is S, because that's the whole base is S, times the height, which is 1/2 S root 3. Well, 1/2 times, and actually the key of this is also put these over 1 to see the simplification. So 1 times S times 1 times S times root 3. Well, the 1's are irrelevant. S times S becomes S squared times root 3. And then 2 times 2 becomes 4. So if I want to know the area of an equilateral triangle, all I have to do is take a side length, like let's say, for instance, S equals 10. Okay. It would be 10 squared root 3 over 4. 10 squared is 100. 100 root 3 divided by 4, well, I can divide 104 into 25. So 25 root 3. So instead of me going through all this trouble of doing the 30, 60, 90 business or finding the height on an equilateral triangle, all I have to do is square the side, multiply by root 3, and then divide that guy by 4. And that's it. So area equals S squared root 3 over 4. S is the side length of the triangle. Okay, now area of a regular polygon. This guy here. This is a little more tricky. Okay, so I'm going to take a little more work to explain this. Basically what you do is you take this figure, you construct the center, and you create however many triangles you have. Okay. Now, all of these triangles are congruent to each other. So the area in this case is really just 6 times the area of a triangle, because that's what we're going to get for the figure. Now, let's just call this S for each side length. Okay, so the area of one triangle, if I just kind of pull this guy off to the side, is 1/2 base times height. Well, the height of this triangle here is really that apothem. That's why we have that figure. The height of the triangle is the segment that goes perpendicular to a side, it cuts in half, whatever the height of the isosceles triangle. It's the apothem. So one triangle is 1/2 S times, we're going to call that A for apothem. Okay, so that's going to be 6 times 1/2 times side times apothem. Now here's where we do a little more fancy work. I'm going to throw that 1/2 in front, and then I'm going to put 6S in parentheses, and then there's the apothem there. Now this 6S, it depends upon how many sides there are. If there are 10 sides, it'd be 10S. If there were 3 sides, it's going to be 3S, however it works out. Well, what is that 6S really? That 6S is the 1, 2, 3, 4, 5, 6 sides added together. Well, when I add up all the side lengths together, 6S is really the perimeter, which we're going to call P. Okay. So the formula, what it really does is says, let's replace this guy with perimeter, because that's what he really is. So it's 1/2 times the perimeter times the apothem. And then just to clean it up a little bit, it sounds better saying 1/2 apothems times perimeter than it does saying 1/2 perimeter times apothem for some reason. So that's the formula, 1/2 apothem times perimeter, area of a regular polygon. But all you're really doing is you're just creating the triangle, and what happens is whenever it's like, if this were 10 sides, it'd be 10 triangles. Well, the 10 sides, the 10 triangles is still going to be that perimeter outside. So we just shorten that formula up, 1/2 times the apothem times the perimeter, done. And they do n times s for number of sides here, but really area is 1/2 apothem times perimeter. Right there, that formula. Nice and neat. 1/2 AP. Okay. Now, for the steps for finding the area of a regular polygon, I suggest you just pause the video here, copy these steps down, and then on the next slide I'm going to show you how it works. So the first thing you do is you create the separate triangles, which is basically what I did in the slide before and I showed the formula. But then what's going to happen is you're going to need to find some side lengths on these guys. So find the central angle. That's the next step. And then step 3, cut the triangle in half. So you'll use its central angle for each of these triangles, cut the triangle for half. The height then of that triangle is the apothem of the regular polygon. And then what happens is the other side that you find is really part of the base. Sometimes you know the base, sometimes you don't, though. It just depends upon the figure. And then find the height of the triangle and the base length. And again, this is going to be what 90% of the work's going to be. This stuff up here is just mechanical. Do this and you're done. And then plug it into the formula to find the area of the regular polygon. Okay, so again, if you don't have it, just pause it, get all these steps down, and then go on. So here's the only example we're going to really do in the video. The rest we'll do in class because they get to be too complex, and it's just easier if I can kind of walk you through and talk you through it. So we're going to find the area of this regular hexagon. We're going to round to the nearest tenth. Okay, so the first thing I want to do, the very, very first thing I want to do is I want to find the 6 triangles. Again, I know the formula is 1/2 AP. Don't even worry about that. This is a hexagon. It's got 6 triangles. Now, some of you are going to say, I don't need to draw them all in. That's fine. I just always do it when I go through it in class. Then I find the central angle. Well, there are 360 degrees total. There are 6 triangles, so each angle is 60 degrees. Okay. And then they've been nice enough here to kind of give us this heads up that, hey, this is the guy we're going to cut in half, because that's the next step. Okay. So I've created the 6 triangles. I found the central angle to be 60 degrees for all 6 of them. Now I'm going to take that triangle, PQR, and I'm going to cut them in half. And this 60 degrees becomes 30 degrees. That's a right angle there. This is 60. Hey, guess what I got? A 30, 60, 90. Now, for this though, this was 5 all the way across here. So now this is 2.5 meters. That's the 30 side. The missing side here is 2.5 root 3, and this guy here is 5 if I want to know him. However, I don't need to. That's all I really need to know. I'd be saying, well, where's this all coming from? Well, it's just one is 30, 60, 90 stuff. But I needed to know this side length here because the whole time this guy was the apothem. Okay, that's why that was so important. The height of one of those triangles, again the book mentions it being isosceles, but really the height of one of the triangles, that's the apothem. So cut it in half to help find it when I realize, oh, it's a 30, 60, 90. So the apothem is 2.5 root 3. Now, area is 1/2 apothem times perimeter. The nice thing is I already had the side length here of 5. So this is 5, this is 5, this is 5, this is 5, this is 5. Whew. So the perimeter is going to be 6 times 5, which is 30. So area equals 1/2 apothem, which is 2.5 root 3 times 30. And it did say round to the nearest tenth, so we don't need an exact answer here. We can just throw in our calculator. So 0.5 times 2.5 times root 3 times 30. So 64.95, which is really 65. Okay, so just to walk through really quickly again what happened in this one. Okay, Going back by the steps. Right. So create the separate triangles. Did that first. Boom. Drew on the other 4 segments to do that. Then found the central angle for each triangle. The reason is I'm going to use that central angle when I come down here to find missing parts of this triangle. Now, next part then is to cut the triangle in half because the height is the apothem of the regular polygon. Well, here we go. I cut it in half. That height here is now the apothem. I did my 30, 60, 90 business, or in some case I'll use trig to find the missing side. There it was, 2.5 root 3. Okay, there's the apothem. Then I go back, find the base length if I need to find the perimeter. I've already got the perimeter though, that was pretty easy. All the sides were 5, so 5 plus 5 plus 5 plus 5 plus 5, or just 6 times 5 is 30. And then use the formula to find the area. There it was, 65 square meters. All right.